When it comes to energy, we should start at the beginning. And for us as human beings in the Milky Way galaxy, that would be the sun. All right, the sun produces a lot of solar energy, and that travels through the vacuum of space, and that's going to hit Earth. It's also going to hit many other objects in our galaxy and in the universe. But let's focus on what it means to us. So the solar energy created by the Earth is going to hit Earth, and primarily it's going to be absorbed by plants. All right, they're going to store that energy as chemical energy. So what originally was solar energy is now contained within the plant. That's why the plant can grow. That's why if you cut down a tree, you can burn the wood, but only for a certain amount of time. There's a certain amount of energy. So the energy that originally came from the sun has actually transferred. It's now inside of the plant, and it's stored as what we call chemical energy. Several different types of energy. We'll take a look at all of them. But just to follow along, the solar energy through photosynthesis has now become chemical energy. Now there's like probably hundreds of thousands of different paths that this energy could then go. I'm just going to show you two examples that I think are more applicable, and hopefully you start to see this pattern of energy and what it's doing as it travels through our ecosystem, through our universe, etc. So one possible path would be that an animal comes along and then eats that plant. So what started as solar energy then became chemical energy. And then once an animal eats those plants, then it's still chemical energy, but now it's chemical energy not in the tree, it's now inside the animal. So whereas the plant could use that chemical energy to grow and things like that, well, now the animal can use that chemical energy to either grow itself or to move or to make noise, anything associated with energy. And we'll look at energy and what it is in more detail in a second. But for right now, just realize it all started with the sun, then the plants converted it to chemical energy, then the animals took that chemical energy and converted it to chemical energy in their own body. Some of you may see what's coming next. Human beings are generally going to eat the animals then, and they're going to then take that chemical energy. So it started with the sun and then was transferred to the plant, was then transferred to the animal, was then transferred to humans. And then once we eat that and gain that energy, then we can do a variety of things. We can use that energy to produce motion. We can use it to produce heat, so we keep our 98.6 degree body temperature. We can use it for sound, so that you guys can hear my annoying voice in all of these videos. But that's all the chemical energy that's in our body that came from the animal, that came from the plant, that came from the sun. Any energy path in our galaxy, if you track it backwards, you are always going to wind up at the sun for the most part. If I come back, that solar energy becomes chemical energy in the plant. Well, it can certainly come down here and go directly to us. That plant could also die. It still has some matter, still has some energy stored inside of it. It could break down. It could, become fossilized or petrified. The same thing could happen with an animal, but they get buried over time. These things become coal. Various different energy sources that we take out of the ground over, hundreds of thousands of years. And once we have that, we can do things like burn the coal to produce electricity, so we get electrical energy. We can use that to produce light, heat, motion. These are all different forms of energy. But the main point here is that what starts with the sun and is radiated as solar energy can become several different forms. Chemical energy in plants, chemical energy in animals, chemical energy stored in like coal or natural gas, things like that. And all of that can further be converted into motion, heat, sound, light, electrical energy, etc. But everything that we use, the lights you use at home, the sound coming from our voice, everything that is associated with energy all originates from the sun. It's kind of fascinating when you think about it. All right, so most of you may have known that. If not, it's kind of interesting to start to realize where everything actually starts from. What we're going to focus on in this class is specifically what's known as mechanical energy. Several different types, as I mentioned, heat, sound, light, etc. We are going to focus on mechanical energy. Now, if we think back to mechanics, which is what we started the course with, when we studied mechanics, we analyzed velocity, time, acceleration, displacement, etc. These are all things associated with the object's motion and its position, so where it is and either where it's moving or how it's moving. So if you remember that and you kind of think along those lines, mechanical energy is just the energy associated with motion and position. So we don't necessarily care in this case when we analyze mechanical energy about light, sound, heat. That doesn't really tell us about how the object's moving or where it is. We only care about the specific energies that are going to talk about an object, where it is, how it's moving. Um, Furthermore, the general concept of energy, and it can be hard to clearly define energy because of how many types and how many ways in which it can be used. But the general definition you'll hear here is the ability to perform work, which is basically, on a very simple terms, is to do things, the ability to get things done. So that can be something like causing motion, generating heat, creating sound or light. These are only a few examples of millions of examples. But just the ability to get things done, to do things. I hesitate to say just to move, but just to do things, to perform work, so to say. And we'll look at what work is in terms of physics. But for right now, energy is just the ability to do stuff. Okay? If you want to do a bunch of stuff all day, like you either have to work, go to school, etc., you want to move a lot of things, you want to heat up your body, you want to talk, anything like that, you need to have energy. We have to eat to get that energy. So just think of energy as the ability to get things done. When it comes to mechanical energy, there's three types we're going to look at. There's two categories, and you've probably heard some of these terms, but not all of them. We have potential energy, and we have kinetic energy. Let's go back again and think about some of the terms we already know and some of the terms we've learned earlier in the year. Potential. If you have potential, it means you could go places, you could do something. But potential implies at a future time. Potential doesn't mean you are currently whatever someone says you are potentially doing or potentially are, but in the future you could be. It's exactly the same here. Potential energy is like the energy that can be used. It's what's known as stored energy. It's there. You have the potential to use that and to, quote unquote, do stuff with it, but you're not currently doing anything with it. And within potential, there's two types. We have what's known as gravitational potential energy, and that's the energy associated with, hopefully you see, gravity. And we have what's known as elastic potential energy, and that's the stored energy that's usually stored in things that are elastic, like springs, rubber bands. Like you'll notice if you pull a spring and let go, it snaps back. If you compress a spring and let go, it snaps back. So as you're kind of changing the shape of that rubber band or that spring, there's certainly some kind of energy stored, because the second you let go of it, it does something. It moves. It launches a marble, something like that. So it's that energy, the potential, it's stored energy that may do something once you either release it or let go of something. And the other is kinetic, and you've definitely seen this term before. Think of static friction, kinetic friction. Kinetic is the case where something is moving. So kinetic energy is just the energy of motion. So if we look at gravitational potential energy, we represent that with a capital E for energy, G for gravitational potential. And that's just basically based on the height of an object. If you think about it, if I hold something above the ground and let go of it, gravity will pull it down. If I'm not really that high, if the height's pretty low, then the energy is low because it can do stuff. It's certainly going to fall, but it's not really going to fall that far. Now, if this was like a heavy rock and I was trying to drop it on a nail, let's say I had a nail and a piece of wood, if I didn't raise it very high and I just dropped it a small height, yeah, it would certainly do stuff. It would certainly drive that nail into the wood, but not very far because I didn't raise it that high. If I take that same object and I raise it much higher and drop it on the same nail, hopefully you realize it's going to drive that nail much deeper into the wood. When the height is high, the gravitational potential energy is high. And that's because gravity has more time and more distance through which to speed that object up, pull it down, etc. So gravitational potential energy, the stored energy that an object has, for the most part based on its height. The higher an object is, the more energy it will have. The lower an object is, the lower the amount of energy. This is why you don't want somebody to drop something on your head from like 3 stories above you. But if somebody drops something from like a centimeter above your head, as long as it's not super heavy, you usually don't mind. Elastic potential energy, the same basic concept, but we're not concerned with height, we're concerned with how far the spring has either been compressed or stretched. And again, if you think about it, it makes sense. If I take a ball and I place it on a spring and I compress the spring only slightly, I can certainly launch that ball when I release that. Stuff will get done, that ball will certainly move, but it's not going to move that high. So my elastic potential energy, EEL, is low because I haven't really compressed it that much. There's not too much energy stored in the spring. Now if I repeat that experiment, but I compress the spring all the way, then I launch it, that ball will go significantly higher. If I compress that spring more, then the elastic potential energy is higher. The ability to do things is much higher. It's going to send that ball much further. So this is really based on the compression, I should say, or the extension of a spring. Whether I compress it or extend it, once I let go, it's going to snap back to its original shape, and I can use that motion to, launch a car, launch like a pinball in a pinball machine, something like that. So I can use that energy to do stuff, but it's stored until I release it. Kinetic energy, energy of motion. Since it's motion, it's based on velocity. You think of a turtle, you're not really scared of standing in front of a turtle as it charges at you because turtles move very slow. The velocity is low, not too much kinetic energy because it's not moving that fast. That's why you look at a turtle and you're like, oh, that's adorable. Unless you hate turtles, then you're like, I hate this thing. Please stop walking towards me. But that doesn't matter. If it's walking towards you at a slow speed, you're not that concerned because if it bumps into you, you're just going to kind of be like, okay, hi, turtle. Whereas a car travels much faster. If its velocity is much higher, it has much more kinetic energy. That's one of the reasons why you don't want to stand in front of a car that's moving very fast. We all know that, yes, bad things are going to happen, but that has to do with the fact that it has so much kinetic energy. So velocity is high, a lot of kinetic. Velocity is low, not that much kinetic. Velocity is 0, you have no kinetic. So 3 different types. Important to realize that gravitational potential energy based on height for the most part, elastic potential energy based on the compression or extension of a spring or rubber band, kinetic energy based on velocity. There's a few more variables that will come into play, but for right now, this is appropriate for what we're going to want to do. So those are your 3 major types. We'll spend the most amount of time with these. The last thing you need to know is that energy is conserved. So if you think back to chemistry, if I had a glass and I hit that with a hammer, well, let's say this glass was made up of 100 billion atoms. Well, after I broke it into a bunch of different pieces, if I took all those pieces and counted all the atoms, I would still have 100 billion atoms. Conservation of matter. You can't end with more matter than you had before. Conservation of energy states the same thing. Energy cannot be created or destroyed. It can only change form. So that means whatever energy I had before something happened must be the total amount of energy I have afterwards. Just like I can't gain atoms out of nowhere, I can't gain energy out of nowhere. If you keep that in mind, this fact that whatever you had before and whatever you had after, at any point in time, those energies have to be the same, there's a pretty unbelievable implication. So we think about this moment just before the Big Bang, okay, somewhere in the universe, the split second before the Big Bang. Well, immediately after, we had some kind of energy in here. Now, I can't answer too many questions about this because scientists don't really know anything before the Big Bang. There's some debate whether the Big Bang actually happened as well. But based on current theories, whatever energy I had before contained in, I guess, what they call this infinitesimally small space, this really, really tiny space, well, a split second later, and again, no, the planets and asteroids and stars and things, they didn't form immediately, but I just wanted to show that after the Big Bang, what eventually led to all the planets, all the stars, everything we see at night, everything we don't know exists, but we know it's out there, we can't see it, the energy that makes us up, that makes the planets up, that makes the stars up, that all came out of this infinitesimally small space. Whatever energy I had before had to be the energy I had after. So all the energy before and all the energy I had after the Big Bang have to be equal. Kind of fascinating when you think about it. The energy that makes up you, me, the computer, the light that you're seeing on the screen, the sound that's coming through your speakers, all of that originated from one specifically tiny point, theoretically, just before the Big Bang. Kind of fascinating when you think about it. Energy before always has to equal the energy after. Really quickly, just to show you how we're going to start to map these energy conservations so we can understand them a little bit better, we're going to use pie charts. So if I have a ball and I'm about to drop it, you'll notice here that it's not moving, no velocity. There's no spring, so there's nothing being compressed or stretched, but I do have height. So all of my energy here, 100%, is gravitational potential energy, which I usually represent as EG, but here I've written gravitational PE. A split second later, when I let go of it, its height has dropped. So I've lost height, so I can't possibly have 100%. It's about halfway down, so I only have half of what I had before. So the question is, if I can't lose energy, whatever I had before has to equal what I had after. Well, if I've lost height and I've lost gravitational potential, how is that possible? Well, I have lost height, certainly, but I've gained velocity. So while I lose height and I lose gravitational potential, I'm gaining velocity, and therefore I'm gaining a bunch of kinetic energy. My total amount, 100%, still has to equal 100% when I add these two together. The difference is I've lost height, so I have half the gravitational potential, and I've gained some velocity, so I have some kinetic. A split second later, I've lost even more height. I only have a small amount, so I should only have a small amount of gravitational potential, but I'm traveling even faster. This object has been accelerating due to gravity, and therefore I have significantly more kinetic energy. So I start with all gravitational. Then I have 50-50 because I've lost height but gained velocity. Then I've gained even more velocity, so I have more kinetic, and I have only a small amount of gravitational potential, so a small amount of EG. So just a way to map out the actual energies. Another example, a bouncing ball. And I apologize, the colors didn't come out very well on this. But I'm holding the ball above a spring this time. Again, it has height, but nothing else. This spring is not compressed. There's no velocity. So I have all gravitational potential. I only have height. Similar to my previous example, once I've dropped this about halfway down, I've lost half my height, so half my gravitational potential, but I've picked up some speed, so the rest must be kinetic. There's no elastic because I still haven't compressed this. In this third case, this spring is fully compressed, meaning the ball is momentarily at rest before it's about to be launched back up. So my pie chart still has to add up to 100, but if you look, it's at rest. I have no kinetic. It is no longer moving. But it is above the ground slightly, so I have a little bit of gravitational, and that spring is now compressed. So the rest of my energy must be elastic potential energy. It's stored in the spring. If I look at this last case, once it launches it straight up, this is now gone. It's uncompressed. This is no longer stretched or compressed. I have no elastic energy. The spring is back to its original state. But I have gained more height than I had previously. I still have less than when I started, so my energy should be less than when I started, but it should be more than I had in the previous example when I was lower, so about half. And since I don't have any more gravitational, I don't have any more elastic, but I do have to add up to 100%, well, I've gained velocity, so my kinetic energy comes back into this equation. So I start with potential, then I have potential and kinetic because I've lost height, gained velocity, then I have elastic potential and gravitational potential because I have a little bit of height and a lot of compression. And in the last example, I've lost all my compression, no elastic potential energy. I've gained some more height, so I have some gravitational potential, and I've gained velocity, so I have kinetic energy. And you'll notice in each one of these cases, using the pie chart, I always have a complete pie chart, meaning I've never gained or lost energy. It's just changed form.